Welcome back. That wasn't rhetorical. Hi. Welcome back. I think everybody's came back. That's always nice. One brief update for you. So on Tuesday, I was expecting to have my office hours in this room after class, and people showed up. Apparently they gave it away. So I have clarified here. It doesn't show my changes. So on Tuesdays, I'm going to hold office hours the same time out there. So outside this room, because there's lots of open places to sit and computers to work at, and it's a great space. And on Thursdays, I do have this room. So after class will be office hours immediately. I changed it this morning, but it doesn't, there it is. Refresh. So yes, office hours on Tuesdays, just outside. So you can find me there. If no one is wanting to talk to me, I will wander back up to my office. So if you show up late to office hours and I'm not down here, then that would be where to check first. My office is in the bridge, 356 between the two halves. So this building is a nightmare. But I'm in between the two, just outside the main office for P&Q. All right. Let's see. Other things on the schedule. I don't have your first formative assessment up yet. That is coming right after class because I wanted to see how far we get. The idea of these is that they should take like 10-15 minutes. So some point between the end of class today and Monday at midnight, log on to Icon and try and do this. It should be questions you can answer off the top of your head about things we've talked about so far. And if you can't answer them off the top of your head, that's an indicator of things that you would want to review. We'll go over them in class. They are not graded. I have not put up homework 0 yet because I was waiting to see if anyone else was going to add and drop, but we will do this in class. Homework 0 will take us about 30 seconds. It's over the syllabus. It's a gimme, just to make sure that everybody knows how to use the system and that I've got everybody's names correct. Otherwise, the homeworks that follow are listed here. If we get behind in terms of content, I may push them back, but I will never move them forward. We make that deal? It will never be earlier than I've said, but it may be later if I need to have a little bit of time. One of the things that I think I forgot to say to this class last time is that on the syllabus, I have a policy here that if you know ahead of time, like you're looking at the schedule and you know like, oh, I'm going to be at a conference this week, there's no way I'm going to get this done. If you email me or contact me at least 2 weeks ahead of time, I will give you an extension on any homework or quiz. If you're planful, I can work with you. It's the last minute extensions that I can't say yes to without making it unfair to other folks. How long the homeworks are going to take, I was asked last time. I honestly can't tell you for sure because what happens is that if you know exactly what you're doing, it goes really fast. And if you don't, then it takes a little bit longer. I do them myself to make sure that everything is correct. And when I do them, I can finish it under an hour, usually, for whatever it is. So the most important thing is to not put it off until the last minute and to ask for help if you need it, because that's what I'm here for. I know some people are afraid of asking for help because they don't want to look silly or whatever. No, they pay me. Did you know that? They pay me to help you. So let me help you if I can. All right. Also, a couple things. No class on the 12th of September. This actually falls right during comprehensive exams. Is anyone having that fun? Anyone?
That's not till January.
Yours is not till January? Okay, well, that worked out well because they were going to kick us out of this room that day anyway. And I will be out of town on this day as well. So just heads up. Okay. So any questions before we jump into some new stuff? So the first topic that I have to go over with you is probably not a new topic. It's a reintroduction to general linear models. And if you've heard this before, then it will go easy. And if you haven't or haven't heard all of it, then I think it's important to go over. Even though you're here to learn multi-level models, a lot of the concepts that show up there that are difficult are linear models concepts that you may have not gotten the way that I wish you could have in your introductory regression or ANOVA courses. In particular, if I said to you a multivariate Wald test, do you know what that is? Ish. Yeah, see, so you're going to have to do those. And it's really tough to introduce new concepts and new models at the same time. So my hope over the next couple weeks is to fill in the gaps that might exist in your knowledge with respect to just linear models in a single level context. Then bring that into the multi-level setting where we'll be on stronger footing to add that unique aspect rather than getting bogged down by linear model stuff. At the same time, I'm also trying to introduce you to how to do things in software, SAS and Stata. I know some of you are probably better at some of these programs than me. Stata, at least one of you said you were an advanced user in the quiz. No one's, someone's like, I don't want to say that. So if you have tips or things that you see me do the code a certain way and you think if you do it this way it's more efficient or whatever, I'm all ears. I'm always looking to improve my programming skills as well, so there's that. So away we go. Here are the topics that to be covered here. So general linear models. This term is an umbrella. It encompasses a lot of more specific instantiations that you may have learned in separate classes. If I had my way, I would not teach this in separate classes, and indeed the class before you, I'm doing all of these things within one context. But if you learned about models for a single outcome variable that's supposed to be normally distributed after you take into account all of the predictors, and you fit only categorical predictors, grouping variables, we would have called that analysis of variance or ANOVA. If you have continuous predictors, quantitative variables, we would call that regression. And if you've got some of the two, we call that ANCOVA or analysis covariance. And then there's the multivariate versions. All of these have in common one thing, the idea that it's a single level model, so for people who are supposed to be independent, and it has a residual that is supposed to be normally distributed with constant variance. That's what they have. One thing just to point out on this, sometimes people get confused about what predictors have to look like, particularly in regression models. Model predictors never ever have distributional assumptions. Have you seen textbooks where they have whole chapters on like data cleaning and transformations and stuff like that? Just wipe that from your memory, okay? Pretend you never ever read it, because predictors don't have to be anything. It's outcomes that are supposed to be normally distributed, but it's the residuals in particular, not the data. So you can have crazy distributions for data that are due to predictor effects. Once you factor those in, normal is the assumption of these models. That'll be the second topic once we get into cluster data is what if it's not normal? Well, then we pick something else besides that kind of distribution to work with the model. So we talked about this briefly last time, the two sides of the model for the means, what you're thinking about in terms of putting in predictors. The predictors in those models have fixed effects that are the same for everybody. The part that we are focusing on most of the semester is the other side, model for the variance. So let's start off. This is a term that you may or may not have heard before, an empty model. More particularly, an empty means model. This is the simplest possible model you could ever entertain. So I have an outcome y per individual, so sub I is a function of beta 0. What's that thing? Constant, or other word starts with an I? Intercept. Yeah, those are interchangeable. And E sub I is my residual. So it's 1 per person. Beta 0 doesn't have an I because everybody gets the same beta 0. If I don't know anything else about a person, what's my best guess for their outcome?
Mean.
The mean, yeah. So that's what beta 0 is in this case. So I have a distribution here flipped on its side. The mean of this distribution is 90. So if I don't know anything else, my entire model for the means, my fixed intercept right here is 90. E is then how far off each observation is. So I'm making a prediction for this person down here. So we're off by 58 in the negative direction. I can then calculate how much variability is left over. And because I don't have any predictors, this is all the variability, right? This is the formula for variance. Each observation minus the mean squared, sum it up over all the people, divide by n minus 1. So empty is a very special term in the world of multi-level models. It's the first thing that we're going to do. You were probably never taught to do this in regression because you don't need a model to tell you how much variance is in a variable, right? You can just ask for descriptives and find that out. But when you have more than one level of sampling, there's more than one kind of variance. So the first step before you think about predicting anything is to get your hands on how much variance you have of each kind. How much variance is across classrooms and how much variance is within children within the same classroom, so stuff like that. So an empty model allows us to partition variance. Right now, there's nothing to partition, but there soon will be. If we were to add a continuous predictor, a quantitative variable here, such as ability, now my model for the means, moving from empty to something that is conditional, meaning it has predictors in it, I've picked up a new fixed effect, beta 1. Beta 1 is nice slope for x, right? Change in y per unit change in x. Beta 1 doesn't have an I subscript. Why? Same reason beta 0 doesn't. Looking for continuity here.
Are you saying because it's not your individual, like it's not, it's a constant?
It's a constant, yeah. It's fixed. It's a fixed effect, meaning that everybody gets the same one. So in this equation, subscripts, by the way, are super duper important in multi-level modeling. That's why I'm hammering on them right now to start with. I used to not believe that, but I am totally a believer now. Y gets an I because each person has a different Y. X gets an I for the same reason. E gets an I for the same reason. Beta 0 and beta 1 are constants. They're fixed effects. When you learned regression, you just called these effects, right? A slope is an effect, but that's not a specific enough term anymore. These are fixed effects as opposed to random effects, which means that each person gets a different version of this. That's what's coming. But the fixed part is where we are now. In this case, we have a new prediction for y that's based on our regression line. So the intercept has moved from 90 all the way down to 29. Why? What does it mean now relative to what it used to mean?
That's the intercept with beta 1 constant.
Close, very close. Not beta 1.
X
X constant at
is the mean.
Zero. See that it would be the mean if you had mean centered it, which is what I'm actually going for here. On my X predictor scale, it looks like it starts at 10 and ends about 40. So what does it mean to have an X of 0? I have no idea, right? It's not possible. So having an intercept reflect my expected outcome for somebody with an X of 0 is 29. That's not wrong per se because the line does keep going, but it's weird because it's a model parameter that doesn't actually apply to anyone in the sample. So right from the get-go, no matter what's going in our model, interactions or not, I'm centering all quantitative predictors so that 0 means something. The grand mean of X would be a lovely choice. That's very common. You could also pick maybe the lowest score so that your intercept is like the lowest possible value of X and then you move that way. It doesn't matter what you pick so long as it's somewhere within the range of the observed variables. Why this starts to matter more in multi-level is that not only are we going to be estimating a fixed intercept for everybody, but we're going to be trying to estimate the variance around it as well. And so we have to have a value that is characterized by data in order to have a good way of estimating the variance around it. Otherwise, the model can actually blow up because it's trying to find something that's not really possible given the data that you have. So the slope is 2. For every additional unit of whatever X is, ability in this case, my Y goes up by 2. So in terms of what's known versus unknown, the horizontal line at 90 here was the prediction from the empty model. I have closed the gap by this much, but there's a remaining gap down to the dot here that's blue. So blue represents variance left over, red represents variance explained, and so now we would differentiate that the blue part is what's known as error variance or residual variance. The red part is explained. And the same formula applies as what we had before. This we've changed what Y-pred means. Y-predicted is what that is an abbreviation for. It's predicted based on the model. Previously the model was just the grand mean. Now the model includes a conditional mean. So this is where the term model for the means starts to make sense here. Literally, if there's nothing in the model, if it's empty, your model is the mean. Once you add a predictor, it's still the model for the mean, but it's a conditional mean. Anybody who has a value of 9, or I guess the lowest score is 9 instead of 10, my bad. Anyone who has a value of 9 has the same predicted value of 32. So it's still a mean in the sense that it's across people, but it's conditional. So synonyms for that would be expected value, predicted value, conditional value. All of those words mean the same thing. It's model-based. What would we typically want to know at this point about the red line here, variance, versus the blue line?
R square.
R square, yeah. What's R square?
It's like a explained variance over like a ordinary variance.
Yeah, how much is explained versus out of the total? We're going to have R squares in this class too, but guess what? If we have more than one kind of variance, we got more than one kind of R square. We're going to have different R squares for different types of sampling variances. So that's where it gets tricky to keep them all straight. If I have a categorical variable, such as something that's coded into binary, then I have the group that's coded 1 is higher by the regression slope. The group that's coded 0 gets to be the intercept in this case. Error variance would still apply the same way. So then, more generally then, fixed effects in the model for the means, these are constants. We're going to focus on having k fixed effects. So in this example, there's 3. The model for the variance we're going to ignore for now, but just know that even though there's an e here, this is a model. It's a model in the sense that this is a choice that you've made. It's not something you have to assume. It's a choice. There are other ones. And if you only have one observation per person and people are independent, this is a lovely choice. Where it can go awry is if the residuals are not actually normal and they don't have constant variance. Then you want a different choice, and that's in the family of generalized linear models. So that's GLM. So does everything I've said so far sound familiar? Excellent. Any questions yet? Yes.
I saw in your empty model you have the degree of freedom n-1, and then the other one n-2 things for the next one, linear regression, you have n-2.
Yes, so n-1 on the first one here, because we have to have estimated one parameter, the mean, in order to compute this variance. When we get to the regression line one here, it's n-2 because we had to estimate 2 parameters to compute the variance. So it's a penalty function. How many things did we have to know over all the possible?
So which means that you have a more complex model, you will have minus more predictors?
Mm-hmm. Yep. Yep. More generally, this term is known as denominator degrees of freedom. It's a function of sample size and model complexity. Yep. Yep. All right. So, one thing that's important to note, when people talk about general linear models, they're almost always pairing it with a certain type of estimation, what's known as ordinary least squares. All the stuff that you painstakingly had to do in intro stat and intermediate stat and whatever else where you're calculating sums of squares and mean squares and cross products and all that shit, that is least squares. Turns out that those formulas work for like this much of all of quantitative methods, right? In the class that I'm teaching before this one, I'm teaching, it's the alternative to intermediate, I'm skipping it. I'm skipping it completely because I don't think it's useful. Because once you get out of this situation where you have one outcome that's normal with constant variance for an independent sample, you can't use least squares anymore. So it's gone. It's gone. We're going to do some other stuff instead. What are we going to do? Maximize. So I'm trying to give you a sense of vocabulary that you may have heard in terms of how model estimation works. So estimation to me is find the numbers. How do you find them? It works out that all you know about least squares is a special case of something more general known as likelihood estimation. That's what we're going to focus on this semester. There are two main flavors of it that we'll talk about in just a second, but this is how multi-level models are estimated. This is how structural equation models are estimated. This is how generalized models for non-normal outcomes are estimated. Everything is run by maximum likelihood. It turns out that there are computational shortcuts that apply that get you into the world of sums of squares for certain cases, but that's it. Then there's also nowadays more emphasis placed on the idea of using simulation. So Bayesian estimation combines maximum likelihood with some sort of prior belief about what your values of your model parameters are supposed to be, and it uses resampling. So all the words in this paragraph have something to do with resampling. You might also throw words in here for things like bootstrapping, permutation tests, jackknifing, exact tests. All that stuff has to do with some kind of sampling. We're not heading here this semester, we're staying here. But where these things start to show up is when maximum likelihood breaks down. When things get too computationally difficult, such as when you have non-normal outcomes and lots of levels of sampling, that's where this starts to break, and that's where the world of sampling through Bayes becomes more important. So maximum likelihood is going to be the name of the game. But just to reorient you to this sort of thing, we have these concepts of how much variance is explained, how much variance is left over, and you were taught sums of squares. Divide that by degrees of freedom. Numerator is the number of parameters you're estimating. Denominator is the number of people left over after you correct for the number of parameters. And then you end up with something called F. We're going to have Fs. We're going to have Fs and Ts, but we're not going to get them through this table. They're just going to show up. So that is to say, your output's going to look different, but what you do with it is the same. And F is still a ratio of what you know to what you don't. Worst case scenario, F is 1. So, yeah, I don't want to have to say too much about that. That's just a little bit of history. Here's where estimation meets terminology meets making sure that people understand what is and what isn't different about what we're doing in terms of estimation. So, maximum likelihood, height, that's the key concept. I see some of you starting to look a little like, I don't like those words. No worries. Do you know what height is? Do you know how to work a ruler? Then you're good, because that's what it is. It's the height of the normal distribution given your model parameters. It's trying to find the parameters that make everybody simultaneously the tallest. That's it. I will be happy to give you more technical details later, but that's all we need to know for right now. What I want to focus on is the two kinds of maximum likelihood that you will have heard of. There is residual or restricted maximum likelihood, and then there's regular flavor maximum likelihood. Maximum likelihood down here is often called full information maximum likelihood. Have you heard that term before? Well, guess what? Both of these are full information. Do you know what full information means? It's good. It's always used in a positive way. It's always used in the context of missing data. That's where that term shows up. Full information just means that you are using all of the original information to estimate your model parameters. That's it. It contrasts with limited information, which is when you first summarize your data and then you do your estimation on that summary. So trying to think of situations in which this would be relevant. Have any of you taken like structural equation models? A few? Well, you were taught in that class that if you wanted to do an analysis on someone else's data, all you needed was their covariance matrix, right? This way for you guys. This is my covariance matrix sign. You need the variances, and you need the covariances, and you need the means, right? And you can analyze their data. That's an example of a limited information. You don't need the original data. When you assume everything is normal, that summary is adequate. Where that falls apart is when not everybody contributed to every variable. If you have missing data, that matrix is not stable. I'll stop there. That's where limited versus full makes a difference. So both of these ways of estimating our model are full information. For whatever reason, ML, which I always say ML in this context, is called FIML, but no one ever says REML is FREML. I'm trying to make that a thing. I'm trying to make fetch happen. Anyone? Thank you. A few of you get that. That's a Mean Girls reference. But I'm trying to make FREML happen because it is full information. REML is the same thing as least squares. They will give you the exact same answers. Least squares is a series of computational shortcuts. That's all it is. The difference is when you have missing data. So if you're doing a multivariate analysis, not everybody contributes every outcome. Leastwise deletion is what happens when you have least squares and not when you have REML. So that's why it becomes important in the context of missing data. REML is what we're going to do in mixed model land for anything that we can, which means models that have normal residuals at all levels. Level 1 is the one that you get the most choices about. The reason we're going to do that is because of this thing that you picked up on, Emily, n minus k, that right there. Do you remember learning about like sample versus population variance, like n versus n minus 1? Someone made you care about that at some point, maybe? This is it. If it's n, it's going to be biased because it doesn't take into account the number of things you had to know in order to calculate that variance. If it's n minus 1, if it's only the mean, it's unbiased. N minus k is the number of fixed effects. So the estimates of the variance that you get out of REML match the same idea of adjusting for the number of things you had to figure out in order to get that variance. It's unbiased. And this matters if you have small samples, where small is the highest sampling level of your model. That's what matters. In contrast, look at this formula down here under FIML. What's missing? Yeah, the minus k. So this one doesn't correct for the number of things you had to find. It doesn't adjust for the number of fixed effects that you estimated. It will be biased in terms of the variances it provides in small samples. So we're going to not do it unless we have to. We have to, though, in certain situations, such as when we switch to models that have non-normal residuals, like binary or count or any of those. There is no such thing as REML for those. For those of you who've taken SEM, IRT, CFA, all of that, that's regular flavored ML. There's no REML for those either. So REML is this special thing that only shows up in the context of multi-level models for normal outcomes. That's the only time you're going to see it. But sometimes the terminology difference, saying that you used REML instead of least squares, throws people off. So let me give you an example. I had a paper I was helping with where someone was doing a repeated measures analysis, like a paired t-test kind of thing, and they didn't have the same observations at time 1 as time 2. And so to avoid list-wise deletion, I wrote in the method section that we used REML, and here's your t-test. And one of the reviewers said, well, they need to justify the use of residual maximum likelihood because that's not what is used in our field. Yes, it is. Same thing. The difference is that I didn't throw away half my data. So there is confusion about that, which is why I want to point out that if you have a single level model, you have one outcome, we're not doing anything different than what you did in regression and ANOVA. If you have missing data or more than one outcome per sampling unit, multi-level data, that's where it differs. Okay? Okay. All right. So we're going to start our review of general linear models using mixed software. This is what we're going to use for multi-level models. You can do all of the things that are lower order in mixed. You can use mixed to run a t-test. You can use mixed to do an ANOVA. You can use mixed to do a regression. an ANCOVA, whatever. All of those are special cases of a more simpler, yeah, let's go with that, more simpler model than what we're going to end up with. But what that means is that your output's going to look different. There's no more sums of squares, there's no more mean squares, because we're in Remel land, not least squares land. There is extra stuff, at least within some packages that Mixed offers, because it's a newer package than what others do. So this is my pitch for why this is helpful. Model implied fixed effects. This is the one thing that Stata rocks at, that SAS is a little bit behind in terms of being able to get these. What do I mean by model implied fixed effects? Extra pairwise comparisons that aren't in your model, simple slopes for interaction terms, that kind of thing. So we'll see lots of examples throughout the semester of this. Model comparisons. So do you remember like hierarchical regression, that concept? Like you have a block 1 and you put in, say, predictors A and B, and then you have block 2 and you add C and D to the list, and then you have block 3 and you add E and F, that kind of thing. And what do you look at between blocks? Why would you not just dump them all in at the same time? R-square difference, yeah, R-square change, right? Because you get R-square at every step. What you want to know is, if I add these extra things, does it help the model as a set? And then you can go in and look at the significance of each thing. Well, turns out you can ask for that without having to do it in steps. That's a line of code for any possible block type comparison. That's a multivariate Wald test. We can do the same thing whether we have a univariate model or we're tackling multiple outcomes at the same time. And all of this stuff looks exactly the same if you have non-normal outcomes in the analog for Mixed across these packages. So it's very general, and it becomes easy to fit any kind of model that you want to within the same program. So, intermediate summary. We're starting with general linear models. We'll practice interpreting main effects and interactions. Interactions in particular is the thing that I'm worried about. We're going to use a slightly different version of estimation that works out to be the same thing as least squares in a limited case, but this will allow us to generalize throughout the rest of the semester. All right. Questions so far? I'm going to reload. I've already had 2 coffees today, so I decided Mountain Dew was not in my best interest. This is a quiet group. Is it the 2 o'clock, like time of day? Yeah, I know, this is sort of a low energy. For me, like I hit my bottom at like 4, like thunk. But I'm still hopped up on caffeine for right now. So we'll persevere. So, reviewing. How do you know if something matters in your model? So every fixed effect that we're going to estimate in general linear models as well as in multi-level models is characterized by these things. Estimate, that's our best guess for what it is. That is sometimes called point estimate for reasons that I don't know. But if you ever hear me say point estimate, I just mean estimate. It's the idea that it's only one number. So without any context, we don't know what that number means. The rest of these values give it context in relation to the variability in the predictor and the outcome. Standard errors. This is something that you typically may not pay attention to because it's a route just to get your test statistic. But standard error by itself is an index of precision. So if I tell you that my best guess for a parameter is 6, that doesn't tell you if that's my best guess out of a bunch of shitty alternatives, like it's relatively best, or like it's a really best guess. Standard error helps clarify which it is. So more generally, if you think about a range of values that something might be, right? Here's my 6. If I have a distribution that looks like this, that's very different than if I have a distribution that looks like this. Mean of 6, both cases. One of them is more certain. One of them is higher, if you will. The standard error is actually related to the change in the slope if you were to move along this distribution. It's related to the second derivative of these functions. That's where it comes from. It comes from calculus. I'm not going to ask you to know that or care, I promise. but just know that it's related to precision, and it's one of the things that the likelihood estimation process spits out as a byproduct of having found the top of the likelihood mountain for each parameter. Estimate divided by standard error is then the next thing that you get, and depending on your program, that is either going to be labeled as a T or a Z. So if you are using Stata without any additional options, which one do you get? Stata people? Z is the default. You get a T if you ask for it. Whereas in SAS, SPSS, you get a T, and plus you get a Z. R people, what do you get? What's default? What's it called?
T?
T maybe? What's the difference?
You assume the population varies
And there's one extra column that will show up if it's called a T, that will not show up if you have a Z. Denominator degrees of freedom. Yep. It's whether or not you're paying attention basically to your sample size. Remember, T is supposed to be for small samples. You get enough people, T looks like Z, and no one cares. So this ratio is called a Wald test. Whether you call it a proper Wald test or a modified one depends on this. If you are ignoring denominator degrees of freedom, it's a Wald test. You treat it as a Z. You don't worry about that as part of your critical value. T, I would call it modified Wald test, and you have degrees of freedom to worry about. In practice, once you get past like 20, it doesn't matter. The difference in your conclusion will be very small. But the p-value that shows up in your output is going to be a function of whether you're using T or Z and denominator degrees of freedom if you're using T. Also, what's nice is a confidence interval. All programs will spit these out. I tend to not print them because they take up extra space on my handouts that I don't normally need for anything. But this, you get to pick, where did 1.96 come from? Yeah, that's the Z value that goes with a 95% confidence interval. So if you wanted a different level of confidence, you'd have to ask it to change this. All right, so more letters that you're going to get familiar with. In addition to T and Z, there's F and chi-square. So we'll use some of these for some things and others for others. So Z is for testing one thing, one parameter at a time. Another way of saying that is numerator degrees of freedom is 1. Like if I'm testing a slope or a mean difference. If I do so without degrees of freedom in the denominator, that's Z. If I do so with denominator degrees of freedom, that's T. If I am testing more than one thing, a set of fixed effects, such as in stepwise regression where you're testing the block of things. Another example of this is in ANOVA. If you have a grouping variable that has more than 2 categories, like if I have 3 groups, that's 2 contrasts between them, and I want to test the set of 2 as a whole, called an omnibus main effect, that shows up in this category here. Z squared is chi-square, T squared is F. So your output from SAS and SPSS and Stata, if you invoke the small sample options, is going to be T's and F's. When we do hypothesis tests involving variances, though, those are going to show up as chi-squares instead. I don't know why, it just is the way it is.
Can I just
Yeah.
clarify? So like in Stata, like when we run like a multiple regression like that, on the result table, like it says T, but actually it's Z.
This is what you'd have to check. Is it printing degrees of freedom? If it's printing degrees of freedom, I would believe that it's a T. But I know in mixed, the default is Z. And in Stata 14, they picked up options for degrees of freedom because you have to choose the way you want to estimate them. And it's like the option DF method in the mixed command. And then when you do all of your like lincoms and margins and things, you have to put comma small to use degrees of freedom.
Because just I checked like in my old like right now, because I remember like it's table says it's T. So then like right now still like it's my observation is like 1,367 it says T in the table, but actually it's Z.
Yeah, so you'd have to look at the documentation that goes with that particular package. I would not be surprised if it's T in regression, and if you fit the same regression model in mixed, it switches to Z.
Okay.
Yeah, you really have to check to know what you're looking for.
Thank you.
Sure. Where'd the standard error come from? Just to keep in mind what goes into this. So it's a function of residual variance left over, and it's a function of the scale of the predictor it's the standard error for. So if I took my variable and multiplied it by 10, my standard error would be bigger by a factor of 10. It adjusts for the scaling. It also is a function of how many fixed effects are in your model. So your standard errors can actually go smaller if you have more predictors in your model that have explained more variance. Where this starts to matter in the world of multi-level is, what do you mean by variance? So if I have a 2-level model, we talked about last time I have 2 kinds of E's, right? I have a level 1 E and a level 2 E. So let's say students and schools. If schools are level 2 and students are level 1, and I want to compute a standard error of something that's related to students, what should go here? Logically. If I'm trying to predict something that's student level, it has nothing to do with schools. Do you think school variance should go here? No, it's not relevant. So student level variance would go here. What happens if you kick out part of the total? Like if we take the school part and set it aside, this standard error gets better. So in certain situations, if you have a level 1 predictor, you can have a more correct and more generous standard error than if you fit the 2-level model you're supposed to than if you fit a single-level model and ignore your clustering. Because the 2-level model partitions out what is variance that's relevant versus irrelevant. And it's reflected in your standard errors. If you have a level 2 predictor, both school level variance and student level variance show up because the bottom level stays here no matter what. So then it would look the same, the difference would be degrees of freedom. So you will see your standard errors change as you add levels to models. The estimates may not, but it's the standard errors that give you the p-values. And all things being equal, standard errors are smaller when you have bigger sample sizes as well. All right, so this idea of multiple fixed effects, I want to show you how this works because we'll be doing this to test differences between models in multi-level land. So it's contrast in SAS, it's test in Stata. So here's an example. Here's an example regression model. I have 3 predictors. If I want to know, on the whole, does this model account for significant variance? That's a reasonable question, right? If this were being run in regression software, that information would be given to me. It will give me the R-square, and what will it give me to go with it? What also shows up to see whether or not your R-square is significant? You probably reported 1 or 2 in your lifetime, I'm guessing. It's one of the letters. F, yeah, F-test. That is a specific instance of a multivariate Wald test. A more general test in this box. Whenever you're testing more than one fixed effect and you're using denominator degrees of freedom to do so, that's an F. Special case of that is the R-square test for regression. So in multi-level model land, you are not going to get an R-square as part of your output because there's no agreed upon universal 1. There's actually different kinds that serve different purposes, and so they don't even give you 1 by default. That means they don't give you an F-test of that either. So Stata does give you an F-test for just whether or not the overall model is significant. SAS does not. But if you want the change in R-square, you'll have to ask for that. So this is what it would look like in SAS. Proc mixed is what we'll use for multi-level models in there, and Stata's down here, so mixed is also. Older versions of Stata have something called XT mixed. These are basically the same thing, although some of the options have switched between the two, but mixed is what I'm going to be sticking with here. Model Y is the first thing here. X1, X2, and X3 are my predictors. By default, in SAS, when you put your predictors in, they assume that they're quantitative variables and they fit a slope through them. In Stata, I believe that is also the default, correct me if I'm wrong, but to make that more explicit, I've used the C dot option in front of each to indicate that they are continuous variables, or quantitative variables. And let's see, yes, so I am making the degrees of freedom method the same as what is done by default, as well as the estimator REML in this. And this is the idea of testing 3 things at once. So this test does not show up by default in SAS, it does in Stata. I want to test 1 beta 1, the weight for x1, 1 beta 2, and 1 beta 3. The commas indicate numerator degrees of freedom. So I'm asking for a combined test. On the whole, do these 3 predictors contribute significantly to the model? Is my R-square for these 3 things greater than 0? That's what I'm asking. This is something that you get already if you have regression software that you will have to learn to get in mixed. That's why I'm showing it to you. And the same thing here. 3 parentheses indicate 3 degrees of freedom in Stata. If you want to do a change in R-square, so this is the idea of blocks of predictors. So you want to know, say in this case, after controlling for x1, if x2 and x3 together help the model. Now, in this context, that may not make sense, but there are certain situations in which this is exactly what you want. One would be if x2 and x3 represented a 3-group categorical variable. Because then, this, as a concept, is group, right? Does group matter is captured by these 2 things. In models with interaction terms, you might have something like x2 is the main effect and x3 is its interaction with something else. And if I want to talk about the variable, I want to lump together its main effects and interactions. That would be another situation in which you might want to test more than one thing. So it's up to you. What you want to test is entirely guided as to what would answer your questions. In multi-level model land, this may also show up as the 2 halves of a variable that is measured at level 1. So for instance, if I had something like students' free and reduced lunch status as a 0-1 variable, the analog to that at level 2, if I had schools, would be the proportion of students in a school that get free lunch. So this one, x2, would be something like, is our math scores greater for kids who don't get free lunch, right? Is being poor bad for you, sort of the question. But then, are math scores on average greater in schools that have more kids who don't need free lunch? So if I want to lump those together conceptually and say, does free lunch matter? That's both, right? That's a situation in which an extra hypothesis test you might want to do beyond demonstrating each of these is to lump them together.
As your interaction?
Not necessarily. This would be the main effect of each, but that would be potentially a 3rd thing, is you could add the interaction. Does the effect of getting free lunch, is it different in schools where there's more poor kids than not? That's what that would answer. And that would be an instance in which I'd have x4, and I'd have a 3-degree freedom combination of those 3 variables.
Wouldn't it just say that the more poor students you have, the more free lunches you have? Is that what that would be?
No, because it's about how it matters for math in this example. So basically it's like, is it worse to be a poor kid in a school with lots of poor kids, or to be a poor kid in a school where there's not that many poor kids? Worse in terms of your hit on math.
So your math scores would have been lower. Yeah, okay.
Yeah, I actually have an example where these are coming from that I'll show you not too far down the road. Turns out it's bad to be a poor kid. This shocker alert. Yes, it's bad to be poor. So, make sure you don't get free lunch because your math scores are just going to tank if you do. I'm joking. All of this stuff is correlational, right? And all of these variables are proxies for other things. That's not my department. My department is this department. But in this case, if I were to lump these two things together to get a combined test of them, Stata and SAS do not give that to me by default. I gotta ask. But it's the same way. So if I just list x2 and x3, then I'm just asking for the unique effect of those two things. And the same thing would be here down here. So that's how we will do change in R-square types of questions in the world of mixed models. And you could have done this in regression land too. They just never taught you it this way. So questions?
So in the previous slide, you have the 3 predictors in the SAS code, and then you include all the predictors. And then in this slide, you have only the last 2, predictor 2 and 1, so which means that in the result section, there will be no information for the R-squared for predictor 1 at all. So you didn't show me the output, so I just can't tell exactly different because on the previous slide, you include the contrast of the 1, 2, and 3, and this one you have a 2 and 3.
Yes.
So in the results section, so for this one, so there will be no information about our x1 at all?
Yes, because this is a different, it's an answer to a different question. It's the difference between R-square per se, which is based on all 3 variables, and this is change in R-square attributable to 2 and 3. That's what this is providing.
Okay, so this one is just the exclude. So okay, that one was a R for all, and then this one is the change from without putting in predictor 1, and then what's the difference between only 2 and versus 3? The R difference, R squared difference. Okay, because I just didn't see the results.
Yeah, so this, if you know what, let me go back. If you know what R-square is with all 3, and you know what the change in R-square is from these 2, right, you can figure out how much, yeah, exactly. So my point is that rather than running these in separate models, like I could have put, I'm just trying to isolate constructs, but I could have taken this line and paired it with this one, and I could do 2 at the same time. So there's no need to do subsets of models. You can ask for what the subset would look like. The only thing that this doesn't tell you is if I have x1 by itself, that's its bivariate effect on y, just like a correlation. When I put x2 and x3, its effect is going to change because it's now controlling. So if I really wanted to know what was the coefficient before and what did it become after, I got to run 2 models to find that out. But if all I want to know is did these things add something beyond that, I can answer that within the question of the same model. Okay. Other thoughts, questions? Yes?
Why don't we specify the small again?
So by the way, this drives me bonkers, okay? Stata people, I hope you're listening right now because I'm going to give you some very practical advice on how to improve your program. So this first line where you specify your outcome and your predictors, everything after the line continuation here, after the comma, are options. So I'm asking for residual maximum likelihood, which at one point in time was not the default. I don't know if it is anymore. I'm asking for variances instead of standard deviations, because that used to also be a default. And I'm asking it to use denominator degrees of freedom, which is the residual method, which is the same thing that is used, what we've been talking about, n minus k. So you would think that when I ask for the whole model using degrees of freedom, that it uses them for everything, but it doesn't. So every post-estimation type command that you add, contrast test, lincom, margins, you have to remind it that you want to use degrees of freedom, and comma small is how you remind it. It means small sample. Is that not dumb? No, really. I wouldn't have put it here if I didn't want you to use it for everything. So yeah, I'm a little perturbed about that. But yeah, that's why. This is Stata 14 and later. Stata 15 is what is in the virtual machine thingies through the university. All right. Okay, so putting in predictors, just a brief overview of that. In the context of regression, most of the time people don't worry about centering their predictors because you can have a constant that's interpretable or not and no one cares. It becomes a bigger deal in multi-level model land because you have to have a variance around that constant in certain models, and that variance needs to be something that can find. So whether or not we center predictors does not affect our square. It does not affect the predicted outcomes. It does affect your model parameters. So the intercept is only meaningful within the scale of the data that you have if each predictor has a meaningful zero value. You can end up with nonsense values for the intercept, but also for main effects of interaction terms. So that's the next lecture. If you may recall, if you have an interaction of x and z, right? The main effect of x becomes the simple effect or the conditional effect when z is 0, and the effect of z becomes the effect when x is 0. And if 0 doesn't exist in the data, both of those simple effects are illogical. They're not wrong, they're just useless. So right from the get-go, every predictor is going to have a meaningful 0 point. So this is why it matters in terms of interpretation. Here's a map. This is an airport map. Does anybody know where this is from? Good guess, but no. This is Terminal B in Atlanta, the ATL. I used to have to go there a lot before Jonathan and I got married when he was working at Georgia, back and forth. I got to know ATL very well. So if I'm getting off the plane and I know I've got 45 minutes until my connection and I'm starving, I go to the map. I find, I like, in Terminal B they have, I think it's Manchukuo. There's like the airport Chinese food is my favorite. That's usually my go-to. But what do I need to know in order to find where Manchukuo is? Where am I, right? Every map has a "you are here" sign. Otherwise, you can't use the map. So to me, this star right here, like I think of data in this context. Like you have a map of your data. The "you are here" sign is your intercept. That's the constant. That's the point of reference that you have to start from. Because when we talk about the effects of continuous predictors, quantitative predictors, we say things like, as x increases, y increases by this much, or as x decreases, right? But how do we know whether we should say increase or decrease? If I'm starting from down here, I don't want to talk about what happens as x decreases because I don't have anybody out there that applies to. So putting it in the middle is the idea of mean centering, grand mean centering your predictors, so that your intercept, your "you are here" sign, is smack in the middle of the data, and you can logically talk about as you go up on x or down on x. But that's not the only choice. If you start here, you talk about what happens as you go up. If you start here, what happens as you go down. But it keeps all of your model parameters interpretable as pertaining to real possible people you could have observed if a 0 value is something that's within the scale of your data. But keep in mind that you are not tied to that location. You can figure out what the intercept would have been for any combination of model predictor, and that is something that every software program can do. Estimate statement in SAS is what it's called, test in SPSS, Lin Common Stata in New and in Plus. So these are statements that allow you to write linear combinations of existing parameters to create predictions, either predicted outcomes or predicted slopes. So here's an example, or not yet, we'll see lots of examples of those. So centering is what we're talking about here, rescaling predictors so that 0 is meaningful. There's only one kind of centering when you have single level data, right? You subtract or add the same constant to everyone's cases. You take your x basically and shift it over. When we get to multi-level model land, this topic is a good month because you can center at a constant or you can center at a variable if you are in lower level predictors, and it completely changes what everything else means. And it's really easy to screw it up, which is why it's going to take a while. But for now, it's nice and simple. I get in the habit of choosing a constant that's not necessarily the mean, but something that's towards the middle that may be a convenient reference value. So for instance, if I had something like years of education, in the general social, what is it? GSS, can't think what it stands for right now. The data set I stole from the book, what is it? Social survey? Social survey, good. I was gonna say social sciences, I'm like, I know that's not right. But I was playing with that data this morning to build your next example, or for the other class, I think it was. And they had mean education was something like, 14.73 years. Well, if I want to put education in a model, I could center it at 14.73, but who the hell is that? Like, no one wrote that down. Like, they got, almost to their junior year and quit? Like, what? No. It would be easier just to pick, 12, because some people put down 12 and say that my reference person, my "you are here" sign, is a high school graduate, or maybe 16, my reference person has a bachelor's degree. Those are equally valid reference points that are in the middle that fill the criterion of a meaningful zero. So if you have a scale where the values mean something, like years of age, years of education, I would pick something that is going to be meaningful, not just the average. I would save the average for variables where no one knows what the scale is anyway, and average is just fine. That's a personal preference, but neither of these is right or wrong. Let's see. So here's what it would look like to request predicted values for a series of different levels of my predictors. So these are basically asking for new intercepts. We're asking the model to provide what the intercept would have been at different points. So for example, if I have x1 that is centered at 10 and x2 that is centered at 5. So note I'm showing that directly in the equation. I will do this as much as possible in our equations in this class because it helps the people reading it know what the reference point is, even if you put it in the text. So I know right now beta 0 applies to somebody who has specifically x1 of 10 and x2 of 5. So these statements down here, this is first one, contrast, is an example of how I get a test of the model R-square, so putting the two predictors together. And then after that is how I would ask it to come up with a predicted intercept for whatever values. So the way that you read these statements is the word here refers actually to the beta that goes with it. So the number is the multiplier of the beta. So beta 0 here doesn't have a variable attached to it. It's an implicit 1. So what I'm saying is in order to get a predicted intercept, I need 1 of the intercept, because I got to start there. Then I need however many that fills in the value for x1 and x2 according to what I'm asking for. So this first line here is actually unnecessary, but I'm including it for pedagogical purposes. If I want to know what the intercept would be for someone with x1 of 10 and x2 of 5, that's what I already got, right? That's the definition of beta 0. So all that I need in this line is intercept 1. If I want it for any other combination, though, I fill in the values on the centered scale. So because x1 I want 8, I have to know what my centering point is. 8 is 2 less than my new 0 of 10. If I want to know x2 is 4, that's 1 less than my new 0 of 5. Now, why would I ever want to do this? Can you think of a situation in which you would want to have intercepts for other values besides the one that you put in the model? I can think of one. Pictures. You want to make a picture? Show what the predictions of your model are? This is how you get your points. Now you could calculate this yourself, right? You could plug these values for your parameters into Excel and build this. That's what I do, right? But then reviewer 3 is like, why doesn't your picture have standard errors? Because I didn't know how to do that part in Excel is not an acceptable answer. You know what this gives you in addition to your point estimate? Your standard error and your confidence interval. So then you plug those into your picture and reviewer 3 is very happy with you. So this, by the way, okay, people who made Stata, as much as I hate your small thing, you totally win on margins because this one line gives me everything that those lines did and then some. They win. Margins wins. And there's also something, there's one more line that you write after it that's called margins plot, and then poof, a picture shows up. They win on that one. So SAS people, take note. You could do better on this. So categorical predictors. That's continuous. Categorical. This is the idea where you have a variable that may have numbers, but the numbers are just labels. So this applies to binary. It applies to nominal. So when you don't have like, favorite type of pet or something, there's just multiple options. It also applies to ordinal. So Likert scale type things. In this case, you have two options for how you put the effect of this predictor into the program. In the next few examples, I'm going to show you both. But we'll start off by doing it ourselves because I think it's useful to learn how to do this for certain situations as well as for pedagogy. We come up with a reference group. We choose it. And we make contrasts accordingly. So for instance, classic example, gender, unfortunately still binary in a lot of data sets because that's how it was collected. This, I will call it dummy coding or reference group coding. Somebody's got to be the 0 and somebody's got to be the 1. Doesn't matter who. The 0 then is the part of the you are here sign of the intercept. The 1 group is the difference from that the coefficient gets. This one I only like to use in very certain situations. You'll see a couple examples of it. It's called effects coding, where one group is negative and one group is positive. You seen this before? Note that I have 0.5 instead of 1. Why did I do it that way? Yeah, Kayla's not sure. She's frowning at me. She's like, I don't know why you did it that way. That's weird. Because what would you normally see instead of the 0.5s? 1s, right? How far apart is -1 from 1? 2. Right? So if I put that variable in the model as a predictor, and I need a 1 unit change in x, but it's going to take 2 units to get to my other group, I got to take my slope and multiply it by 2. No, I'm not doing that. I don't do math, ever. Ever. So yeah, I picked plus or minus 0.5 to keep it a 1 unit difference. But do you know why I don't like this way in most cases? If I put this new variable, this plus or minus 0.5 into my model, who's my intercept? Exactly. Somebody who doesn't exist in this binary variable land. The you are here sign does not apply. I don't like that. There are certain situations in which this is useful, but this, I would argue, is not one of them. So if we have, say, a 4-group variable, that requires 3 contrasts, right? If I have a 5-group variable, how many contrasts? Yeah, you guys know this part, right? So if I were to make the contrast myself, this is a classic way of doing it, dummy coding, where I've designated control as my reference. They get a 0 in all 3 of these new predictor variables that I'm creating. They are my you are here sign. And then each one designates the difference between control and each of the other treatments in turn. So when you put these 3 new variables in the model, they're binary. They are treated as continuous. That's not a problem because there's only 1 unit between them, so fitting a slope between 0 and 1 isn't weird. But even though they're categorical in your head, the program says they're continuous. They all have to go in at the same time, otherwise it doesn't give you the right answer. So if I tried to do some sort of stepwise something, and I just stuck in D1 here by itself, look at what that means. It's the average of control, treatment 2 and treatment 3 versus treatment 1. That's not what I wanted. So they all go in at the same time. Of the four groups here, how many possible pairwise comparisons are there that I might want to make? 6. How many am I going to get from this model here? 3. How do I get the others?
Redoing it.
Redoing it. That is how I learned as well. Yeah, so you make a new reference group, you get some of the missing comparisons, and then you make another reference group and you get the last missing comparison, right? Not anymore. Nope. This is another example of model-implied fixed effects. You can ask for the missing comparisons out of the same model. So here's how the model gives us what the mean is going to be for each of my groups. Given this coding system that I have right here, the treatment 1 mean is the intercept plus the difference between control and treatment 1. Treatment 2 mean is the intercept plus that difference. Same thing for 3, right? If the model tells me what the mean is going to be for each group, then it is capable of telling me what the mean differences are for any of these. It goes like this. So the first 3 are directly given by the model as the effects of D1, D2, and D3. That's control versus each of my 3 treatments. The other 3 possible pairwise comparisons are linear combinations of those fixed effects. You got to ask for them, but you can ask for them all from the same model. Yeah. A side note on philosophy before I let you guys go. So have you heard of like family-wise error rate, the thing that's terrorizing the nation? You heard this term before? It always shows up in this context. No one gives a shit about family-wise error rate in a regression model with 20 predictors, but all of a sudden it matters if your predictors are grouping variables. I don't understand why. But these 3 are given by the model. If you want to go in and do post hoc comparisons, what are you supposed to do? Worry about error rates, right? Bonferroni and Tukey and other dead white guys like that made stuff up that we still do, right? No. If the model knows these 3 and it knows these 3, I don't see the 3 that come out by default as being any more likely to have type 1 errors than the 3 that you're asking for. 1 in 20 is wrong if you're at alpha 0.05. So to me, when we do these sorts of things, I am not going to worry about additional alpha correction thingies for model-implied fixed effects. By putting these 3 terms in, you have got permission to look at any combination that you want. That is my philosophy. Others may disagree, but I'm just telling you up front, I'm not going to worry about this. If you look at 20 things, 1 is wrong. The things that show up by default don't get any special privilege to me over the things you ask for. So, okay? Why not? All right, we're done. Any questions before we adjourn? All right, then I will stick around for office hours. Question before we adjourn? Yeah.
Yeah, for the readings, there's like a place where you, like it says course textbook, and you click on that and go like copy book or whatever, which I did. But for some of the other ones, like your text to Hoffman 2015, or should we buy those too? Because that's only used on a few days, and then all these other ones.
They're all
on the site, and I just don't see it.
They're not on this website because someone would yell at me. They're inside Icon.
Oh, okay.
Yeah, I gave you all my book chapters. I don't need you to buy my book.
I thought you said that, but then I was like, I don't see it on here, so maybe we do. I don't know.
No, thank you for clarifying. No, I think I would get in trouble with copyright issues if I put it all free. And so that's why it's inside the course documents section of Icon.
Okay.
All the readings are. Just not the Snyders and Bosker book.
Oh, yeah, I have that.
Okay, so. All right, I will send you an email as soon as your first formative assessment is ready. And otherwise, have a great weekend.